Okay, now let's look at how to find the equation of a line in 3 space. Let's take 2 points. Remember, 2 points determine a line, and this can be in 3-dimensional space. Let's let that be A, x1, y1, z1, and let that be B. And let P be any point on the line, so we'll just call it x, y, z. So P is not fixed, but A and B are fixed. So let's let A, so let's go down here and draw the axis. And A is the vector representation of AB. Let's say a vector AB. So that's going to be x2 minus x1, y2 minus y1, and z2 minus z1. So it's in the same direction, same length as the ray AB. So, one fact is that the point P, or any point P, is on the line AB if and only if AP and AB are parallel. Now, why is that? Okay, here's AP. Now, if AB is over here, then P's not on that line. Okay, and the starting point on both of those vectors is A. So either AB is here or AB is here, but it's a line, so it extends in all directions. So AB has to be parallel to AP because they have the same initial point. So, you can't think of it being parallel like that because this point here and this point, these 2 points have to be the same. So it's not that's parallel. But in order to lie on the same line, those 2 rays have to be, or vectors have to be parallel. So if you remember, 2 vectors are parallel. That's an important fact. If they're scalar multiples of one another. I.e., for example, vector u is t times v, and t is a scalar. Or we could say AP, the vector AP is t times a. Okay, remember our line here is A, B, and P is the point of the line, so AP and A is the vector representation, which is down here, so they have to be parallel. They're in the same direction. That means they're in the same direction. So, AP, its vector representation is x minus x1, y minus y1, z minus z1, and A is A1, A2, A3, let's say. So we get, each component has to be equal. We get x equal x1 plus A1t, y equal y1 plus A2t, and z is z1 plus a3t. And these are called the parametric equations of a line. They all represent one line. And the vector A is the direction vector. It tells us what direction this vector is going. So for an example, let's find the parametric equation for the line through the points, through these points. Okay, the first thing you have to do is find A, the direction vector, and that's just the vector representation between the 2 points. So that is 2 minus a minus 3, 5 minus 1, and minus 2 minus a minus 1 gives me a minus 1. So that's the direction vector. That's the direction the line's going. And so all we have to do is say x is equal to x1 plus a1t. So x is you can pick either point. You could pick this point or you could pick this point. Let's pick this point. So x1 is -3. Here's a1 plus 5t. Y is y1 plus a2t. So here y is 1 plus 4t, and z is z1 plus a3t. So z is -1 minus 1t. So these are the parametric equations for that line. And let's look at another example. Find the parametric equation for the line through 2, 0, 1 parallel to the vector -1 to -3. Well, if the line is parallel to this vector, then this is the direction vector for the line. So that's our A. So then all you have to do is just go x is x1, a1 plus a1t, so 2 minus t, y is 0 plus 2t, and z is 1 minus 3t. So we have these parametric equations for the line. So you can let t be anything, and that will give you a point on the line. Let's look at it this way. Let r be x, y, z, the vector, where x, y, z is any point on the line. And let r1 be x1, y1, z1, and that's the fixed point on the line. Okay, so if I draw a picture, here's P1. Here's x, y, z, and here's the origin, and here's the vector r. R goes to the point x, y, z, and here's r1. Now if we go, let's say -r1, then this vector right here is r plus a -r1 or r minus r1, so that makes this vector r minus r1, the vector between P1 and P. So the vector P1P is the same as R minus R1, which is parallel to A, the representation vector, which is down here somewhere. So R minus R1 is some scalar multiple of A, so a vector R is R1 plus TA. This is the line. It's the same thing we just talked about, traced out by the tip of the vector, or the terminal point of the vector R. So see, R changes as you move. So if this is R, this is R, this is R, depending on T, then this gives you points on that line. And it forms a line. And it's also the line through the point P1 parallel to the A, which is the direction vector. So this is a good way to think about it right here. It's a line traced out by the tip of that vector, because if you let T be anything, that just gives you a point, any point on the line. Okay. To show if two lines intersect in R3, or are parallel, or if they're skew. Skew means they're not parallel and they don't intersect. So it's like when you're on the freeway and the bridge goes over it, they're not necessarily parallel, but they don't intersect either. So those would be called skew lines, or skew. Okay, so if they're intersecting, to test if they're intersecting, you set the corresponding x's together, the y's and the z's. So I'll just say you set the corresponding equations equal and see if there are scalars, T and S, that satisfy all three equations at the same time. What I'm talking about is the x, y, the three parametric equations, x, y, and z. If they're parallel, the direction vectors, A, for each one, must be parallel. So that means they are scalar multiples. So let's see an example of this. Here's one line, and here's the second. So L1 is this, L2 is, and the scalar in the second is V. So the two scalars are T and V. Okay, so the x's have to be equal, so we'll set these equal in the first two equations and see if what we get satisfies the third equation. So what I'm going to do is I'm going to do this by elimination. I'm going to multiply the first equation by 2, and that'll get rid of my t's, and then add them together. So I have 2 plus 1 is 3. The t's will drop out. This will be 8 minus 1 is 7. minus 2v plus 6v is plus 4v. So minus 1 equals minus 4 equals 4v. So v is negative 1. Substitute that back in here to find my t. 4 minus the negative 1 is 5. So t is 2. So see, we're going to see if these intersect or parallel or skew. So we take these two equations right here and we set them equal. We try to find the scalars that satisfy those two, which we did right here. And now we're going to check them in the third equation. So we take these over here and substitute them in and see if they're equal. So is 5 minus t equal to 4 plus v with the scalars we found. So t is 2, and v is negative 1, and 3 equals 3, so they are intersecting. Now where do they intersect? All you have to do is substitute this v and this t into any of the line equations. So let's substitute into line 1. So we get x equals 1 plus 2, t is 2, so 5. Y is 1 minus 4 times 2 is negative 7. And z is 5 minus 2, which is 3. So the point that they intersect is at 5, negative 7, 3. Or you can take v and substitute it back in. It doesn't matter which one you do it, because it has to satisfy all three equations. Okay, if these were parallel, then 2, negative 4, negative 1 would have had to be a scalar multiple of the other direction vector. These are the direction vectors for the line. So this is for line 1, this is for line 2. Those two direction vectors would have to be scalar multiples of one another. All right, let's move on and talk about planes. So let P1 and P2 be points, fixed points. Then all points P such that P1P, the vector P1P, is perpendicular to P1P2 lie on a plane. So you have 2 points. And there's a vector P1, P2. Now, if you want all the points orthogonal to this, that's the right angle, that's going to be all the points lying in this plane, and that plane is orthogonal or a 90-degree angle. This, say, is coming out of your paper, P1, P2, but all these are the P1Ps, and they form a plane. So that's how we're going to think about that. So we're going to let A be the vector representation of P1, P2, and so since that's perpendicular, then their dot product has to be 0, so because A is going to be perpendicular, so A dotted with P1P has to equal 0 since A is orthogonal to P1P. So we have a1, a2, a3, dotted with x minus x1, y minus y1, z minus z1, and that's equal to 0. So I have a1 times x minus x1 plus a2 y minus y1 plus a3 z minus z1 equal to 0. And this is the equation of a plane. Where x1, y1, z1 is a point in the plane, and a, the vector a, is called the normal vector. It's perpendicular to the plane. Okay, so here's an easy example. And we want to find the equation of the plane through the point 2, negative 1, 0 with the normal vector negative 1, 2, 3. So all we have to do is it's a1 times x minus 2 is the point plus 2a2 y plus 1 or y minus y1 plus a3 z minus z3 or z1 equals 0, and just multiply this out. We have minus x plus 2y plus 3z, and the constant is plus 2 is plus 4. So we have x minus 2y minus 3z equal 4. There's the equation of our plane. And notice the coefficients of x, y, and z here. X, well, before it changes the sign. So if I had this in the form ax plus by plus cz plus d equals 0, a, b, and c are the components of the normal vector. So if I had this all on one side, then I would have components of the normal vector. And now it's still normal. It would just, even with the sign change, it's just that it would be in a different direction. Be pointing down instead of up. Okay, another example. Find equation of the plane through these 3 points. Okay, well, let's find the vector representation from P to Q. So that's 2, negative 1, 6, and P to R is negative 3, 5, and 1. So, I mean, if you have a plane is determined by 3 points. So PQ and PR are going to be in the same plane, so is their vector representation. Well, their vector representation is going to be perpendicular or parallel to the plane. So if you remember, I'll write it down if you don't. A cross B is orthogonal to both A and B. So we need the normal vector here. Alright, so we're going to do, let's let this be A and this let B, and we want to find their cross product. Remember, we cross out column I, cross out column J, and cross out column K. And what we get is negative 31I minus 20J plus 7K. So that is our normal vector. So N is minus 31 minus 20 and 7. And we'll take P for our point, and our plane equation is going to be minus 31, x minus 4, minus 20, y plus 3, plus 7, z minus 1 equals 0. And when we multiply that all out, we're going to get and multiply by a negative. That's the equation of our plane. Okay, two planes are parallel if their normal vectors are parallel. Okay, so we have a plane here and a plane here. They're parallel because the normal vectors are right here and right here, so their normal vectors are parallel. And if they're not parallel, they intersect in a line. And the angle between the two planes, if they intersect, is the angle between the two planes is the angle between their normal vectors. Okay, so remember cosine theta is the dot product of the normal vectors divided by their magnitude. We learned that recently. And also, let me write down this theorem because this is kind of important. You should know this. The graph of ax plus by plus cz plus d equals 0 is a plane with normal vector a, b, c, which are the coefficients of the x, y, and the z. Okay, so now we're asked to find the angle between the two planes. So find the angle between the two planes okay, N1, the normal vector for the first plane is 1, 2, negative 1. Those are the coefficients of x, y, and z. And the second, the normal vector for the second plane is 2, 1, 0. So the angle between them is found by using cosine theta. We take the dot product of those two, which is 1 times 2 plus 2 times 1 minus 1 times 0, which is 4, over the magnitude of N1 is 1 plus 2 squared plus 1 is 6, and the magnitude of the second one is 5. So it's 4 over the square root of 30. When you use your calculator, that gives us theta is 41.2 degrees. Okay, so that gives us the angle between two planes. Um, let's go back to lines for a minute. I want to go back and get what's called the symmetric equation of a line. And all you do to get this is you eliminate the scalar t. So we get rid of t, and what we get is x minus x1 over a equals y minus y1 over b equals z minus z1 over c. And AB. Well, actually, we can use A1, A2, but I didn't use that up there, so I need to do A, B, C. And we call ABC the direction vector of the line. So it kind of gives a direction of the line. So let's look at another example. Find the symmetric equations for the line of intersection of the two planes. Of the above two planes that we just finished talking about. We got the angle between them. So first thing we need to do is find a point on that line. And the easiest one to find is we're going to set z equals 0 to find where the planes, and if both planes intersect there, the line intersects there too, where the line intersects the xy plane. So we had x plus 2y minus z equal 2 and 2x plus y equal 1. Those are our two planes, so here we have x plus 2y equal 2 and 2x plus y equal 1. Multiply that equation by negative 2 and add them. So we get y equal 1. And if y equals 1, we plug it in here to that equation, and we get x equals 0. So here's our point. X is 0, y is 1, z is 0. So that gives us a point on the line. Well, the line has to lie in both planes. I'll call it line L is in both planes because it's the intersection line. And L is orthogonal to both normal vectors. Remember, the normal ones are orthogonal, so if it's orthogonal to something that's orthogonal, it has to be flat or it's in that plane. So it puts us back in the plane if it's orthogonal to something that's orthogonal. So we take the normal cross product of the normal vectors to get a vector that's orthogonal to them. and that gives us a direction vector. And so symmetric equations, all we need was the direction vector and a point. So we have x, and we're using the symmetric equation. So it's x minus 0 over 1 equals y minus 1. We're using the point 0, 1, 0 along with this direction vector. So we get x equals 1 minus 1. And we're done. All right, look at some of the example homework problems for some more solutions.